Chapter 9.
I'm talking about this chapter.
Chapter 9 is an interesting chapter because for some people you will catch on very, very quickly and move through the chapter without too much trouble. Others, especially if you struggle with geometry and algebra, both, or specific parts of either one of those classes, this section can be a pain. So, first thing I want to talk about, we're going to look at some algebra topics you need to make sure you guys are pretty solid on, and then we'll look at the actual trig stuff for this week. First thing I want to mention, and this is a potentially vague question, so listen carefully and think it through. When you're solving an algebra problem, I mean any algebra problem, there is a list of acceptable and common steps you can do. One more time. When you're solving an algebra-based problem, there's a list of acceptable steps and common things that you can and should do. We need to talk about that list because when it comes to sections from this chapter, those are going to be some big things we need to put together. All right. Let's start about our list. Here we go. If I hand you an algebra problem, think of any algebra problem you've ever done in your entire life. There are some steps you can always do. Let me start off with a couple that we should all know. You may add, subtract, multiply, or divide to both sides. As long as you get to both sides, this step is always and forever allowed. You may add 3 to both sides. You may add 5 to both sides. You may subtract 7 on both sides. You may multiply by 2 on both sides. You may divide by 5 on both sides. You may add, subtract, multiply, or divide on both sides with a couple of very small exceptions. When it comes to division, you want to make sure you never divide by 0. And you want to also avoid multiplying by 0 because that tends to get rid of it. So, think back to algebra. It's a very vague topic. I'm asking for a reason. You're given an algebra problem. What are some things that could pop up? What are some things you've done in the past? Factor. Exponents. Along with factoring, you might say distributing, right? The opposite of it. So you could factor an equation or you could distribute into a parentheses. What else? Square roots and squares, right? In fact, in algebra, especially when it came to functions, there were formulas to simplify some of that, and some you had to do by hand, right? If it's square rooting a number, you could do one set of steps. If it's square rooting an equation, there were slightly different steps you had to do. Okay? What else?
Graphing.
You could graph it, right? Look at the properties from the graph. Not a common one that a lot of people like, but it is possible. We could do it. And one that we will talk about a little bit in this section, but not much.
Say no more graph.
You're right. We won't graph by hand.
That's fine.
Right? That's what I said. What else? Again, this is meant to be vague. Okay? A lot of things we can say. We could, but let's put it on the list anyways. Right? But how about I go farther than that? What if I just said, generic simplify? Right, if there's parentheses and stuff, like, maybe I can get rid of those parentheses by doing some simplification of some kind. That's big for our category, but it's there. Right? We could do something to the variables. We could move the variables around. We could add the variables, subtract the variables. We could apply rules to the variables themselves. We could input a new variable if we wanted to. Not always very helpful, but it could be done. Like, it's always allowed.
Well, logs.
Logs, exponentials. Algebra 2.
I still don't really understand
No, I didn't even do anything in class.
Oh, I know.
To me?
Oh, I know.
Why is it my fault?
Because we cover it in college algebra, and I remember barely covering any of it because I was like, well, we're done with the year, so great. What else?
Bull. You said by Riley.
How about this one?
I wrote from across the room. That's kind of loud.
A common one that we don't do nearly enough. Combining like terms or combining fractions. When you're in like elementary school, we talk a lot about combining terms and combining numbers. But as you get towards more algebra, this becomes less common, but we'll come back. Anything else we can think of? By the way, this is a great list so far.
Exponents, multiplying exponents, all that. Right?
Yeah, there's also these.
We've already used this.
There's also like the extra rules that go with this, right?
Yeah, there's also rules and like theorems and equations.
Right. There's a bunch of those little pieces that come in together, right? Cool. Now I want to also mention one last thing. Most of these apply to both sides. But there's a few that apply to one side at a time. That's really important for this to get through today. One. So the first piece is guaranteed you have to do it to both sides. So you have to have two sides of an equation to work with. A lot of parts of this chapter that will not be a luxury that we have. We will not be able to add and subtract to both sides because we won't have both sides. We'll only have one side. So this first one, nice, not really useful. Number two, we can do that to one side. You can take one side of an equation and factor it. You can take one side of an equation and distribute it. That is easy to do. The square root square root also usually applies to both sides. If it's not applied to both sides, it usually fits into the category of simplifying something. Like the square root of 49, that's simplifying. Graphing, again, is usually assumed you need both sides, so you can set it equal to something, so you can graph the equation. Doing stuff with the variables depends on the context, so it could be some, it could be others, so I'll give it like a half circle. Logs and exponentials, especially the rules, those usually don't apply to logs and exponentials, but those rules you can do on one side. Now, lucky for us, we don't deal with logs and exponentials in this class, so yes, know that they exist. For us, we don't really do them. Combining like terms and combining fractions, that can be done to one side, and therefore will be good for us to talk about.
So we're gonna try to figure out the other side.
Yes. So, this chapter of trigonometry is it's interesting. So, there's an idea called trigonometric identities. In fact, if you have your little cheat sheets, they have a bunch of them on there. We're going to look at alternative ones and show how some of those actually work. I'm actually going to do a little proof today. That being said, for this class, some parts of it may feel like a proof, but not as strongly structured. We're not going to be doing two-column proofs where we sit there and say, here's our statement and our reason, and this is where each one goes. No, we're not doing that. Instead, the nice part of this section is, I will tell you the beginning and the end, much like a proof, where you know what the end solution should be. And the part that makes it like a proof is you're tasked with finding how to get there. What steps are necessary to take, how to do so. Now notice on the sidewall over here, there's a step of 4 that I recommend pretty strongly for this chapter. It's also the same 4 that the book represents as well, but you'll notice that this thing primarily deals with working one side of an equation. It's the very first thing it recommends. That is because if you do not work with one side of an equation, it becomes very, 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 very difficult to actually get anything useful out of it. So at this time, what I'd like you to do is take out your cheat sheet. I want it out this entire week. If you've lost it, I will find you a new one. Get it though. You do not want to have to rewrite all of these sheets down. So that will be your other option. What I'll begin with today is I will be going through and showing a formal proof. One of only a couple I will do in this class. I am doing a proof. This proof will be showing the first big set of trigonometry you need to know, which is referred to as the Pythagorean identities. There are 3 versions of this particular theorem. I'm going to use these steps we have circled on the board to show its options. And with those steps, you'll figure out how to show those three theorems are true and fit a variety of categories. As I said, if you look at the section that we're going to be talking about, a lot of it deals specifically with how to get from one section, one writing of a version of a trig function to another version. You have to understand each of these theorems and the pieces to them in order to do that. Like I said, some of you will find this very, very easy because it's like a puzzle. You're trying to fit the right piece to go and find your next step. Some of you will find it very difficult because you don't know your pieces very well. It's like looking in a box where there's no pictures. So, let's talk about the Pythagorean identities. There are three of them. The reason they're called the Pythagorean identities is because they're all based upon the Pythagorean theorem. And for this, I'm going to do our first proof in the class. Identities.
These are already on paper.
Whew. Yeah, they are. There are three of them. They should be listed as follows. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And cosecant squared plus 1 equals cotangent squared, I believe is the other one. I always get one of them backwards.
How do you always remember stuff like that?
I don't. I just messed one up.
I know, but
Yeah, that's a long time. It's my job. I get paid to do it. If I don't get paid to do it, I probably wouldn't remember it. So, I'm going to prove these first three theorems. I'm going to prove how they came together using only these steps which we know work algebraically. Now, that being said, you don't have to know these proofs. The big thing is I want you to know that these three statements are true because we're going to base them upon true things. That is the point of a proof and a theorem, is you should know it is true when you are done. You don't always have to remember the exact way to get there. Okay? That's the big idea. You don't have to remember the necessary steps in between for these particular proofs, but you should know that because I have shown the steps, that what I say at the end is in fact true. And so what I said first, I'm going to prove in class in front of you today, much like a beautiful magic trick, that sine squared plus cosine squared will always equal 1. This is a true statement. If you take a calculator out and type in sine squared of 30 plus cosine squared of 30, it will always equal 1. You type in sine squared of 0 plus cosine squared of 0, it will always equal 1. Type in sine squared of negative 5 or 6, and negative 5 or 6, it will equal 1. No matter what number you pick, no matter if it's in radians or degrees, it does not matter, it does not care. This theorem is true. So let's prove what? Now the reason it is called Pythagorean's theorem is because it is based on Pythagorean identities because it's based on Pythagorean's theorem. So step 1, I'm going to reference something that is true. Welcome back to proof class in geometry. Step 1. Like I said, in this class we will not be doing proofs. We'll be instead doing trig identities. They're much simpler, much slower pace, but the same concept will go through every time. We'll always start with something we either know to be true or is given as true in the problem. I want you to take a look and follow along as we go. You are not needing to put this in your notes. I want you to understand it. If you are just copying it down and don't understand it, then you are wasting your own time, more so than normal. Here we go. First thing I know to be true. According to trigonometry, the Pythagorean theorem states as follows: O squared plus A squared equals H squared. If you prefer to write it in A, B, and C, that also works as well. I just prefer the trig version because I like it better. We know this is true. It has to be true. Pythagoras proved it about 3,000 years ago. For any right triangle, this statement is true. Now what I'm going to do, I'm going to use that first trick. Since I do have two sides of an equation, I may add, subtract, multiply, or divide as long as I do it to both sides. Now, normally in algebra, you do it with numbers. I am smart, and you are smart too. If you can do something with a number, you may also do it with a variable. So you can add or subtract, multiply, divide by 3. You can add, subtract, multiply, divide by 7. You can add, subtract, multiply, and divide by pi. You can add, subtract, multiply, and divide by x, as long as x isn't 0. You can add, subtract, multiply, divide by anything you want as long as it's not 0. So, first step. Step 1. We know this is true because of the Pythagorean theorem. Step 2. I'm going to do something very unique. I'm going to divide both sides by a number. The number I'm going to choose is not 3, it's not 5, it's not -6, it's not -4/3. It is h squared. I take both sides and divide everything by h squared, which I know is allowed. Again, I can add, subtract, multiply, or divide as long as I do it to both sides.
I don't like doing stuff like that.
Me either, but it's necessary for this particular problem. It is weird.
So how do you know, like, what?
Well, in this case, I could, if I needed to, draw a picture and pretend these are numbers. Like think of h as 5, o is 3, and a is 4. Use a simple Pythagorean triple. And it would still work. All right. If I do this, I get this nasty fraction. So I take step 2. I divide by h squared. Step 3. I'm going to distribute, which I'm allowed to do as long as I do it to everything. So I'm going to take this h squared and divide it to each individual term. This is allowed mathematically. So I take my third step. Levi, you are on a roll today. So I take it and distribute that division problem to each term.
And now I only have one side.
What is that? That's one.
All right. Next piece. So one more time, I started with something that we know is true, Pythagorean theorem. I took an algebra step I know what I can do. I divided by both sides. I took an algebra step I know I'm allowed to do. I distributed that problem to both sides. Next step. I'm going to factor. I'm going to factor lazily using a property of exponential functions. This property states that if I have a function that is being squared on top and bottom, it is equivalent to factoring the square out of that function. Step 4. I'm going to take the square.
Nice one.
I'm going to factor the square out. So it goes O over h squared, a over h squared, and h over h. This right-hand side, I have not simplified yet. I can simplify at any point. In fact, you know what? Let's do it now. Anything divided by itself, as long as it is not 0, is 1. And you know what? That last piece is actually really important because I need to know that it's true and know that it doesn't apply here. I can take anything divided by itself and it equals 1 as long as it's not 0. But h can't be 0 because h is the side of the triangle. The side of the triangle should never be 0. All right, so I end up with this equation. So I factored. I factored in a weird way, not the way you would typically do in algebra class, but I did factor. All right, now, step 5. I know something to be true about 2 of the things I have in this problem now. O over h is known in trig. So is a over h. Opposite over hypotenuse is what in trig?
Sine.
Sine.
Cosine.
Whoa, that's cool. Man, what's wrong?
Dang. Is that it?
Step 5. We know that sine of theta is equal to O over h. We know cosine of theta
That's exactly what it
is a over h. And you know what? That's on our list. It's our first Pythagorean identity. Which means that if I mention this particular identity, you should know it is as true as the Pythagorean theorem. You know it's true, you know it works.
So you have to use the trig version of the Pythagorean theorem, or you're not going to know.
Or it gets weird when you get to that last step.
Yeah.
Now I could always convert the last step, because if I did the last step the other way, it'd be a over c plus b over c. But those, remember, are just opposite and adjacent respectively. So it still works out. Now, this is one version of this answer, but algebraically, I could do anything I want with this problem and still get to what I need. Example. This is one version of the problem. What if I applied rule number 1? I have two sides of an equation. I can add, subtract, multiply, or divide to both sides. Let me focus on those first 2. Adding and subtracting. This is version 1, which is on your cheat sheet. but it is not the only one.
We're going to prove the next one now.
In a second. Alternative versions of this one. So we're going to call these 1A. What if I move the sign? Sign's a number. So I should be able to add, subtract, multiply, and divide to both sides.
Cosine squared equals 1 minus sine. Right?
This is another version of the same exact Pythagorean identity, which will be helpful for our problems. Another version, as you can imagine.
Could you put this into a side?
Yep.
Cosine.
So, your cheat sheet does not list these two, but it's on that list.
Is those the only things you can do?
Will we be using those?
Well, it turns out there are other things you can use.
Oh, you could like square root it and then.
Yes, but those start to get real nasty. And there's some versions that are on there. In fact, this is the most basic fact of trigonometry. Before this point, we've been doing applications of geometry primarily. The graphing portion, you're graphing a trig function, which is great, but this is where we start to get to the real meat of trig, using trig functions to do something. We have now officially proven 3 versions of the same problem. That using Pythagorean's theorem, we know these 2 trig functions are related. Now, I want to prove the second one real quick. Now the second one, I'm going to go a little faster, because you're going to notice there's a certain theme to these. They all kind of fit together. Because all I did was, I chose to divide by something. For the next one, I'm going to choose to divide by something as well, just something different. Now, to do the next couple theorems, you notice that at the end, I had to use a very specific definition. That sine was equal to over h and cosine was equal to a over h. The other trig functions should also be known by now using either SOHCAHTOA or the inverse rules. Meaning if you don't remember the definition of cosecant, it's on the page. You should look it up. If you don't remember the definition of secant, it's on the page. You should look it up. Let's go to number 2. I believe on your cheat sheet, the second version of this problem says 1 plus tangent squared, or is it tangent squared plus 1? They're the same thing, right? Tangent squared plus 1 equals secant squared. So, problem 1, let's prove this second one. Now, like I said, it's going to have a very similar feel to it, very similar flow. In fact, I'm actually going to save most of my work. Remember, I did not require you guys to write these down, so I can cheat some. All right. Erasing step 3, 4, and 5. Those are useless. Now, Levi, you made a very excellent point when you said it's weird to divide by h squared, but I can do it, right? It's just a number. I chose a number that was in this problem because I saw later on that it was eventually going to cancel. So what if I chose a different number? I chose h squared for the last problem. What if I didn't choose h squared? What if I chose o squared?
Oh my god, I'm good.
Well, in this case, o squared gives me the third one. What if I chose a squared?
One of the words feeling is going to be on our test.
Oh, it won't.
It's going to be like a bonus question, I know.
Actually, every year that I've had this class, I have done one proof on the test saying prove one of the 3. I'll pick that one. And it's always a bonus question.
Yeah, I know. I'm kind of happy that these kind of make sense.
They do kind of make sense. And they're much easier versions of what you typically did in geometry, which I think is nice, because geometry ones are like scary you, haha, evil. And then Trig's like, not so bad.
Geometry, there's like 40 different new rules for the freaking theorem.
All right. We're going to prove tangent squared of theta plus 1 equals secant squared. Are we ready?
Yeah.
So just like with the previous one, I have selected a term to divide by, in this case, a squared. I could have chosen a, but that would not cancel.
Wait. Okay.
Okay, just like with the previous one, step 3. I'm going to distribute this a squared to each term. And when I distribute, something unique happens. So I end up with o squared over a squared plus a squared over a squared equals h squared over a squared. Step 4, I'm going to factor again. I will also cancel at the same time. just like I did on the previous one. So step 4, factoring. I factor my function. This becomes O over A squared. A squared over A squared. As a reminder, anything divided by itself is 1, provided it is not 0. But A is the side of a triangle, so it can't be 0. So this becomes 1. This becomes H over A squared. And now we have to pull some definitions out again. Step 5. The first one is referred to as a quotient definition because it involves division. O over A is tangent. So Katoa. But what about H over A? H over A. It's going to be one of the alternative ones because the H is on top. So in this case, it is secant. You notice it is a flipped version of cosine. Cosine is A over H. This is H over A. So I use secant. Secant. The left-hand side becomes tangent squared plus 1. The right-hand side becomes secant squared, which is exactly what we thought it would be. We are finished.
Yes.
Which means this statement, tangent squared plus 1 equals secant squared, is just as true as a squared plus b squared equals c squared. In geometry, that was the original point of a proof. You start with something true, and if you follow true steps, you end with something that is equally true. So if a squared plus b squared equals c squared, then tangent squared plus 1 equals secant squared.
Did we divide h squared on the last one?
On the first one, h squared was what we divided, yes.
I thought it was just h.
Nope, it was h squared. That's the only way, because that forces something to cancel. This is a common trick when you're doing a proof problem. If you ever go to an advanced proof theory class like ACAP, which is a lot of fun if you like proofs. If it's not proofs are not your thing, you will hate yourself and everyone you've ever met. You will curse your mother.
Did you say there's a whole class of only proofs?
Yes, ACalc, advanced calculus. It's only proofs.
Do you have to take that?
Nope.
Okay.
Only if you're a math major. And boy, is it fun. Recommend it every day. That was the best class I ever took. I cried.
Did you really?
Yeah. Never seen a grown man cry?
Mr. Douglas cried because of a math class. The guy that can do like
Yeah, no
3
kidding.
quadrillion.
That class was the best class I ever took. I loved every second of it. I cried because I was so happy. I finished a 12-page proof.
What class is it?
ACalc, advanced
Oh, so
calculus.
it was happy tears.
Oh yeah.
A 12-page proof?
Yes.
One of these that's 12 pages long?
Yes.
To prove one thing?
Yes.
No shot. What was it?
I'll bring it in.
What?
I'll bring it in for you. It's actually in my portfolio of things to show off if I have to get hired somewhere. Okay, so now we know this statement, number 2, is true. It has to be true. We know it because we used the Pythagorean theorem to do it. We took all appropriate algebra steps to get there. So this statement has to be true. But again, just like the previous one, this is one version of this proof. There are 2 alternatives. These are not listed on your sheets. Let's go through them. Alternative number 1. I move the 1 over. So I could have something like tangent squared is equal to secant squared minus 1. That is an alternative version of that exact same theorem. Second version, a little less interesting. 2b, or not 2b, whatever. I move the tangent over. I end up with 1 equals secant squared minus tangent squared. And again, these are not new, they're just rehashing the old. So if you ever see one of these in a problem, we can perform an algebraic operation referred to as substitution. If I ever see tangent squared in a problem, I am allowed to substitute it with secant squared minus 1. That is a true definition. If I ever see cosine squared in a problem, I am allowed to, we write it as 1 minus sine squared. That is allowed. Because we know it is true. Now, the third one, you can imagine, Very similar. Choose O instead, or O squared, and you will eventually get to the third formula. It works the exact same way. Again, the concept is very straightforward. The third version. Number 3, on your page, should be 1 plus cotangent squared equals, yeah, I was raised writing it this way. Another algebraic property is that I can reorder addition at any point in time. So I can do 1 plus cotangent, or I can do cotangent plus 1. They're all the same thing. And 2 alternative versions. 3a, 3b. 3a, I move the cotangent number 1 equals cosecant squared minus cotangent squared. 2, cotangent squared equals cosecant squared minus 1. There are 3 of these formulas listed on your cheat sheet. All 9 of these are true. They are all true because they follow algebraic manipulation directly from Pythagorean theorem. That is why they are called Pythagorean identities. Again, the big 3 are on your cheat sheet. All 9 are true. Now, before we go on your cheat sheet for today and for this week, there are a few of the other facts listed on that cheat sheet that you need to know in order to do the problems for this week that we'll be doing in class. Every day we come in, we will have problems that we will spend the majority of our time on. There'll be very little lessons from me at the front for the rest of this week. Instead, we'll do little activities, we'll try out different things, try to treat this like a little bit different of a class. These 3 are the foundation, the building blocks. Other ones that need to be known. Yeah, they're all on there. The reciprocal identities.
That's not Hayden.
So, you need to know the reciprocal identities and the Pythagorean identities, including their alternate forms. One last set. These are ones that are not on there. Beautiful. Fine. Okay. So these 2 are on the list. Should be your first big flap on that cheat sheet. As you might imagine, we're going to go through every part of that cheat sheet during this chapter. Now, the part that is not up there. This is one that I told you about back in December. I recommended many of you put it on there. If you have not done so, this is one I would strongly recommend you add on. These are referred to as the quotient identities. There's only 2. They are very easy. And they are tangent equals sine over cosine. And cotangent equals cosine over sine. For the rest of this week, the next 3 days, this list will become this world. Every day in class, we'll use one or all of these identities to solve a problem. Now, if you're the kind of person who was really good at the algebra side when it came to the number part of it, this may be a little bit different. Because we will have very few numbers involved in any of the problems we're going to talk about for this week. Most everything we're going to talk about revolves around using identities in a variety of ways. In fact, take a look at the very first problem we'll do together before we finish class today. It is the only problem we're going to do today. And this is what your homework for this week that we'll be doing in class looks like. You are asked to prove. In other words, show the reason why this is true. It's a very simple concept. Here's your first one. It is show that tangent times cosine equals sine.
What would we turn these in?
Not this one, but starting tomorrow,
Wait, this goes in our notes.
this is your notes. You may use any of this three lists with identities.
It's worth like $1.40.
Reciprocal identities, the quotient identities. You may use any of the three to do so, as well as any and all algebraic steps that you may be feeling is necessary. Now, for this one, take a close look. I'm going to follow through on the 4 steps on the wall over there and talk about why each step exists and how to show it to use this kind of problem. This is not a proof problem. This is referred to left-hand, right-hand problem. I have told you the 2 endpoints. You have to get me there. Picture this is Google Maps. You tell it where you're starting, you tell it where it's finishing, Google Maps fills in the rest. You are now Google Maps. You tell me the directions to get there. I tell you, hey, start at cosine and tangent. And it's sine. Show me how I get that. So to do so, I recommend the first thing you do,
Divide by cosine.
first thing everybody do, work with only one side at a time. And try to choose the most complex side as the one you're going to work with. Why? The more complex it is, the more things you can do. The sine, there's not a lot you can do to sine. Sine is just sine. But cosine and tangent, there are ways to rewrite one or both of those. There are ways to manipulate one or both of those. You can do things to both of those. The more complex side, that's the side you're going to start with. So in this case, the first thing I'm going to do, I'm going to start with tangent times cosine. And at this point, I only work with these two. I do not touch sine at all. Sine is where I'm supposed to end. I have to figure out how to get there. Now, to get there, I can use any of these three. But my recommendation is, especially the more complex the problem is, at the beginning, the second step isn't nearly as useful. But as we go farther, it is better. Look for things to factor, distribute, square, or combine fractions. If I don't have any of those in the problem, then I skip step 2. Step 3. Use your solution as a guide. Pay attention to the solution. You can't jump straight there, but know that's where you're trying to go. So if you see yourself getting pieces, like I know tangent is 1 over cotangent according to the reciprocal rules. That helps me none, because cotangent isn't in the answer and it doesn't get me any closer to the answer. This takes practice. It takes skill. It takes finesse. It is not easy for some at the beginning. For some, you catch on very, very quickly, which is great. Enjoy that. If you're in that other category, be patient with yourself. This is new. 4th thing, if all else fails, there are ways to convert everything into sine and cosine. The quotient rules. These can convert anything into sine and cosine if you try hard enough. Between these and the reciprocal identities, everything eventually becomes sine and cosine. Not maybe in a weird spot, but it's there. So, let's take a look. We start with tangent times cosine. So you guys already know the first step. A little bit thick. I have to find a way to somehow convert tangent times cosine into something that simplifies into sine. Here's what I'll do.
You need some find tan.
I'm going to rewrite tangent using my quotient rule. Here's how I do it. Tangent becomes sine over cosine. So what I did was I replaced the tangent function with something I know that tangent is equivalent to. Tangent is equivalent to sine over cosine.
Oh.
Now it's kind of obvious what happens next.
And then you just, because the cosine would cancel out and you just put the sine.
There's a property of algebra which states that something is on the top of an equation and the bottom of an equation. You may cancel them. Cosine is on top. Cosine is on bottom. So they cancel. Meaning these two are the same. How do we know that? Because tangent is equivalent to sine over cosine, and the cosine cancel.
Is that it?
This is a trigonometric identity.
So we're done?
That's it. We have found the pieces that get us from start to finish. Like I said, I told you where we're starting. I told you where we're finishing. You have to fill in how we get there. That middle piece is all the work you have to do for today and easy. Because you have to figure out what step can I put there in the middle to get me there. And obviously, on easy ones, there's only one step in the middle. The more complicated the function is, the more steps might appear there. For today, we're going to know. Same concept. It'll be simple, but the idea is there. We're taking a function, modifying that function using things we know to be true, in an attempt to rewrite it in the form we know it should be in. And I told you there might be some small graphing. If you are not convinced these two are the same, graph both sides separately. Graph tangent times cosine on a calculator, use Desmos, and then graph the sine function. They're the exact same thing. They graph the exact same way. They have to. Because they're the same. Again, gosh, that's enough, because this is where people get kind of weird, because they're like, I don't understand what we're doing here. Your job, I told you the beginning, I told you the end, your job is to get me there. That's you. Show me steps why it works. Show me steps that make me know how it works. It has to follow true algebraic steps or it doesn't count. You can't just be like, oh, it works. I'm smart. I know it works. You gotta provide some rationale, some reason as to why it does in fact work. Here we go. Example number 2. Proof. Cotangent
Times.
divided by cosecant is equal to cosine.
Can you just come up with this in your head?
No, that cannot, no human I have ever met can do these off the top of their head, like creating them. Some can do them without, seeing the steps. Like I can do a lot of the simple ones really easily without needing extra help, but like you cannot just be like, clearly this is true. Obviously, no, I used the book. This is an example in the book.
Well, one you could do is just the cotangent times sine equals cosine, because it's just the opposite of what we just did.
So, one more time. I have told you the beginning, cotangent over cosecant. I have told you the end, cosine. You must figure out what goes in the middle that makes this true. Because it's not obvious these two are the same thing. Not to you. If I graph them, they're the same, so I know they have to be the true. But how do I get there? What information do I put in between these two? So let's apply our steps. As a reminder, step 1, start with the most complicated side you can. They both look equally complicated, pick one. And be willing to switch if you find it's not working. Okay? In this case, most of them will be obvious which one you should start with. So I'm going to start with this complicated one, cotangent over cosecant. Okay. I have to apply some kind of rewrite, some kind of system to somehow turn this equation into cosine. Now there are a few alternatives to how you want to do this. It depends on each individual's algebra skills. So I leave it to you guys. If anybody thinks they have a good idea of what they think the first step should be, shout it out. Common one. I like it. The common one is to go ahead and jump straight to step 4. Step 4 says, if possible, convert everything into sines and cosines, which I will now do. So cotangent is cosine over sine divided by 1 over sine. So she used a quotient identity for the top one and a reciprocal identity for the bottom one. So again, I have done nothing that is not allowed algebraically because I start with something I know is true. I replace it with 2 things that I know are also true. So far, this is actually decent. It looks worse. It's not. But somehow I have to fix this. What happens next? So, beginning algebra skills, either the signs cancel or you have to perform rewrite. We will continue from here tomorrow. Everything?